This video introduces the topic of absolute value equations and absolute value inequalities. The learning outcomes are to solve absolute value equations and to solve absolute value inequalities. Before solving absolute value problems, we will quickly review graphing absolute value functions to gain a better understanding of what it means to find solutions to absolute value equations and inequalities. Let's begin by graphing the function f of x is equal to negative absolute value of the quantity x plus 3 plus 2. First, we need to recall the parent function graph of absolute value as well as our transformations. We know that the absolute value function is a V-shaped graph with the vertex at the origin. The transformations include the following. The negative is a vertical reflection, so we know that our graph will open downward. The plus 2 on the outside of the absolute value symbol will cause the vertex of the graph to be translated 2 units upward. The plus 3 inside the absolute value symbol is a horizontal shift 3 units to the left. Remember, we set the inside, the x plus 3, equal to 0 and solve for x. When we do this, we see that x is equal to negative 3, and negative 3 is located to the left of the y-axis. So the vertex of our graph will be located at the point negative 3, 2, and our graph will open downward. To complete the graph, we notice that there is no horizontal or vertical compressions or expansions, so we do the slope of 1 and negative 1 to complete our graph. Let's take a look at the x-intercepts of our graph. Notice that this is when the y value is equal to 0, so we are looking at the zeros of the graph. Notice that the zeros are also known as the solutions when we set the equation equal to 0. We can see them as the x-intercepts here and here on our graph. Depending on the transformations of our absolute value function, we can have our graph touching the x-axis only at one point. The vertex would be on the x-axis. Another scenario of transformations can have our graph never passing through the x-axis. The vertex can be above the x-axis and opening upward, so that the graph does not have a 0. The vertex can also be below the x-axis and opening downward, and again, the graph would not have a 0. Let's return to our equation and set it equal to 0. This will allow us to solve for x and find the zeros, the x-intercepts, algebraically. So we let negative absolute value of x plus 3 plus 2 equal to 0. To solve absolute value equations, we first need to isolate the absolute value symbol. So we need to subtract 2 from both sides and multiply both sides by a negative 1. We now can solve the absolute value of x plus 3 is equal to 2. By definition, absolute value means the distance a number is from 0 on a number line. So we have the situation where some value, the x plus 3 value, is 2 units from the 0 on the number line. This means that our expression of x plus 3 can either be 2 units to the right of 0, or it can be negative 2 units to the left of 0. This means that we need to set the stuff inside the absolute value symbol, the x plus 3, to equal to 2 as well as negative 2. This will give us 2 linear equations to solve. Solving x plus 3 is equal to 2, we find that x is equal to negative 1. Solving x plus 3 is equal to negative 2, we find that x is equal to negative 5. We can plug these values into our original equation and see that both answers make the statement true. Both are solutions to the equation. Our solution set, then, is the set of negative 1, negative 5. Please check out the special case video that solves an equation containing 2 absolute value statements equal to each other. I will guarantee that this case will be on the test for this unit. Let's turn our attention to absolute value inequalities. Similar to quadratic inequalities, absolute value inequalities can have different as well as special scenarios. Let's take a quick look at these scenarios using our knowledge of graphing absolute value functions. When dealing with inequalities, remember we need to pay special attention to the inequality symbol. Less than and greater than inequalities will have open circles for the x-intercepts, while less than or equal to and greater than or equal to inequalities will have closed circles for x-intercepts. Let's say we have an absolute value graph with two x-intercepts. If we make this into an inequality, we can say we want the x values for when the y values are greater than 0. We can see that y values greater than 0 occur to the left of the leftmost x-intercept, as well as to the right of the rightmost x-intercept. This will give us a solution with two intervals. If we wanted the values for which the y values are less than 0, we would only have this interval, the section between the two x-intercepts. This should remind you of the quadratic inequality solutions. Let's look at another absolute value graph with one x-intercept. Notice that this will divide the number line, the x-axis, into two intervals. If we want y values greater than 0, we would have all of the x values, maybe except for the vertex of the graph. If this is a less than or greater than, the vertex is not included. If this is a less than or equal to or a greater than or equal to, then all the x values of the x-axis or all the real numbers would be the solution set. Finally, let's look at an absolute value graph with no x-intercepts. If our vertex is above the x-axis and opening upward, we can clearly see that the entire graph or all the y values are greater than 0. And the solution set for the inequality is greater than 0 would be all of the x values. Thus, the solution set is all real numbers. But for what x values will the y values be less than 0? Since the y values will never be negative in this scenario, the solution set would be empty, as there are no x values for which the y value will be less than 0. Now let's get back to our absolute value equation and change it to the inequality of negative absolute value of x plus 3 plus 2 is greater than 0. First, we need to solve for the x-intercepts, the zeros of the associated equation of f of x is equal to negative absolute value of x plus 3 plus 2. Since we already found the 0 for this equation, we graph them on the x-axis or number line with open circles, since we have a greater than inequality. Now we can test x values from each interval into the original inequality to see which values make the statement true. So we pick a number between negative infinity and negative 5. Let's pick negative 6 to test. And we're going to place this into our equation of negative absolute value of x plus 3 plus 2 is greater than 0. And we find that we have negative absolute value of negative 6 plus 3 plus 2 is greater than 0. Simplifying, we get negative absolute value of negative 3 plus 2. That means that's negative 3 plus 2, which is negative 1. And negative 1 is not greater than 0. So this interval, negative infinity to negative 5, is not part of the solution. With this information, I would assume that the interval on the far right is also not in the solution. Let's check to make sure. Pick a number between negative 1 and positive infinity to check this far right interval. Let's pick 0 and plug it into our negative absolute value of x plus 3 plus 2 is greater than 0. Solving, we will find that we have negative absolute value of 3 plus 2, which is equal to negative 1, and negative 1 is not greater than 0. So, as we suspected, this interval is not part of the solution set. Let's pick a number between negative 5 and negative 1. I'll pick negative 3 and plug it into our inequality. This will give me negative absolute value of negative 3 plus 2, and we can see that that equals to 2, which is greater than 0. So this is the only interval in the solution set. Because we have open circles, our solution set is the open parentheses of -5, comma, -1, close parentheses. Let's take a look at the graph of the inequality. Here, the original graph of the equation, f of x is equal to a negative absolute value of x plus 3 plus 2, that we graphed earlier. The inequality states that we are looking for y values of the graph that are greater than 0. We can see that the graph is above the x-axis for the x values between -5 and -1. We cannot include -5 nor -1 as these values will cause the equation to equal to 0, not be greater than 0. This concludes this video.